call Dr. Gaurav Bhatnagar and Janki Ghosh on the stage. Please, sir, ma'am. I would like to request Professor Janki Ghosh to be a chairperson for this talk. Now, just a small introduction about Bhatnagar, sir. Gaurav Bhatnagar is a visiting scientist in the Indian Statistical Institute. He is interested in studying how Ramanujan could possibly have discovered his identities and in multiple series generalization of Ramanujan's identities. Earlier, he worked in Educom Solutions Limited and led the development of Educom Smart Class, a product used in thousands of private schools in India. He is the author of Maths Concepts, a book for middle school published by Penguin in 2008. So I would like to request Gaurav Bhatnagar, sir, to start his talk. Please, sir.
Thank you very much. Thank you very much. Can you hear me? And for the invitation for this conference. It's a beautiful campus and I'm really enjoying myself. I'm glad to see some children there. So, the net products of for whom we are working. So I'm going to talk about Punya Mishra's mathematical ambigrams. This is joint work with Punya Mishra. Punya is a professor in education in Michigan State University, and he's better known as one of the co-founders of the TPAC theory. So the TPAC framework, rather, is for teacher education using technology and in the classroom. And this is his side interest as an artist. And then we have been collaborating on a series of articles in a magazine called At Right Angles, which you must be familiar with. Here's the abstract. Very briefly, ambigrams. So this is about ambigrams. Ambigrams are a way of writing words or phrases so that they can be interpreted in multiple ways, and they demonstrate various kinds of symmetry. So the abstract is something that you can read. What I feel is that sometimes in classrooms, one just sticks. Often we just stick to the mathematics. And often that involves, doing some concepts which are sort of meaningless to students, which are some procedures. I can remove this one. Can you hear me without the mic? I'll just speak a little louder. Okay, so there are certain mathematical ways of thinking. There are certain things which give us certain jokes, mathematical stories, and now we are adding some mathematical art to it, which I feel that teachers could use in the classroom. You can tell your students that this too is somewhat mathematical. It is not solving equations or this or that, but these are also motivations which many of us mathematicians had when we started studying math. To be able to find such jokes, like I say, in the thing. So let me begin with some. So all the graphics in this talk are made by Punya, except for one, and there is copyright. So can you read this? So if you reverse it, if you rotate it, it again still reads ambigram. You see that? So this part becomes the M. Very good. Okay, so this is a ambigram of the word ambigram. So you can see it has to be cleverly made. Some graphics, and this is something which children can enjoy doing, doodling in class and figuring out how to do certain things. Here is one we made for the magazine. Can you read that? On the top, what does it say?
Right angle.
And what does it say here? The magazine's name is At Right Angles. And if you see if you flip it across this right angle, you get the same thing. So it has symmetry across this line y equal to minus x. So one of the purposes or one of the approaches, one of the thoughts that we had while we made a lot of these ambigrams was that they should represent the idea in multiple ways. So the idea is of course right angle, and the form should match the function. So here is another one which I am going to do on the isosceles triangle. So here's a common problem: prove that base angles of an isosceles triangle, which is a triangle with two sides equal, are equal. So you have a triangle and the base sides. And there was a standard proof which was quite long, and then at some point somebody programmed a computer to find the proof. And what the computer did was something remarkable. It just put a mirror in between the two triangles. So it proved that ABC is congruent to ACB by using SAS, and then that proved that the corresponding angles are equal, and corresponding to angle B here is angle C here. So B equal to C. So that's how they did it. And based on that, we made this ambigram and we modeled this thing. Can you read this? Isosceles. Okay, I should mention those people who are taking pictures, you don't really need to take pictures. There is a magazine which is available free of cost. It's called At Right Angles. All these things appear there along with descriptions, which you will find useful to, it's available online for free. So there's a lot more stuff over there, of course. So I do encourage you to download the magazine. It's called At Right Angles. At Right Angles. So if you do a Google search, you'll find it. Okay, so a small poem we wrote on this. So this is also a fair activity, we thought, that you can ask students to write. So there is a proliferation now on the web of mathematical poems, and teachers around the world did ask their students to write poems on mathematical concepts, and they came up with very nice ones. So this one, for example, is about this proof that I just described. An isosceles triangle looks in the mirror and finds itself unreversed, and base angles are equal. So the proof is more. So this is also an activity, I would say mathematical activity, where you're trying to communicate mathematics using poetry or using graphics. Okay, here's another story which is quite, a lot of us know about the Fibonacci numbers. So the Fibonacci numbers are 1, 1, 2, 3, 5, so on. Each number is the sum of the previous two numbers. Right? So 2 is 1 plus 1, 3 is 2 plus 1, 5 is 3 plus 2, and so on. The ratio of the successive Fibonacci numbers, they go to what is called the golden mean. So the golden ratio is such that A plus B is to A is same as A is to B. So you have golden rectangles, and you have a golden spiral, and here is an ambigram for the golden spiral, which fits inside a golden rectangle. So a golden rectangle is, take a rectangle such that if you remove the largest square, which is this part, you get whatever remains is also in the same ratio. And can you read it? This is G-O-L-D-E-N. Golden mean. So it's spiraling into. Can you read it? Okay, so again, this is a rectangle. If you remove the largest square, you get another rectangle. Remove the largest square, you get another rectangle. Keep going on, and then a spiral is formed. An infinite kind of spiral is called the golden spiral. So again, a different ambigram. Symmetry. So a lot of ambigrams are about symmetry. So in mathematics, there are multiple ways in which one looks at symmetry. The first way is related to graphs in the coordinate plane, which should say plane, not plan. And the second way is from notions of congruence. So we'll look at both ways. So symmetry across graphs. So we have concept of even functions, which mean symmetry across the y-axis. Odd functions, symmetry across the origin or x-axis. These are not functions but graphs. Symmetry across the line y equal to x. So you have two functions which are inverse functions. So the way to understand symmetry is, of course, looking at these points. If this is AB, this is A minus B. This is symmetry across the x-axis. Similarly, this is symmetry across the y-axis. This will be symmetry across the origin. And then AB to BA is the symmetry across the line y equal to A. So if you have an equation and you replace interchange x and y, you get some symmetry. If you interchange y with minus y, you get some symmetry, things like that. So interchanging x with y gives you inverse functions. So here are some examples of functions. This is an odd even function. It's even, it's called even because y equal to x square, x raised to the power 4, x raised to the power 6, so on. They all look like this. And there is a symmetry across the y-axis. And similarly, this is called an odd function, y equal to x cubed, x raised to the power 5, so on. They're symmetric across the origin. So if the point is over here, there's a symmetric point over here. So if you put a line y equal to minus x, it will be symmetric across that. That's fine. This we cover in calculus every year. So here's an example of a parabola. An ambigram for a parabola. Can you read it? Huh? Yes, no? So the symmetry across here is completely even. So if you see, there's a symmetry across the y-axis. It is shaped like a parabola. It reads parabola. So multiple ways of saying the same thing. Here is the one for mathematics, which is extremely symmetric. It's in the shape of a circle, just symmetric across x-axis, y-axis. So these are called chain ambigrams. So you make a chain out of the ambigram. This is the graph of a hyperbola, which is an example of an inverse function, which is the same. Y equal to 1 over x, its inverse is also the same. So it's symmetric, so we made one for inverse. The shape of a hyperbola. So again, I'm repeating, there's really no need to take photographs. All these things appear in a magazine called At Right Angles. You get much better graphics. Okay, so hyperbola. This one is more interesting. Can you read this? So this is the exponential function, this is the log function. They are symmetric across y equal to x because they are inverse. So this ambigram is x and becomes log. You see that? So if you take the x and you reflect across this line, you get the log. X-axis or y-axis? ambiguous. It's an ambiguous ambigram. So there is an X here. There's also a Y. It's on the Y-axis. Read Y-axis. So since this is the Y-axis, I would go with Y-axis. Yes. So again, if you notice the A and the S, it's very cleverly done. Okay, is this better? Okay, so x-axis, is it better now? Yeah, it's better now? Yes, sir. Okay. But it's on now, not better. 0 and 1. So this is x-axis. Then the other approach for symmetry is through notions of congruence. So congruence, of course, is when two objects in the plane are considered congruent if they are superimposed on each other. So you can move one and put it on top of the other. And this concept leads to the concept of groups of symmetries of objects. So for example, here is a set of symmetries of a triangle. So you take. Oops. This is working. So you take a triangle and you rotate it by 120 degrees, and then you can flip it like this. So it becomes 2. So rotate it in this plane, and all of them together they form a group. So you keep doing them, they will get back the same thing. So for example, you do this once, twice, and if you do it third time, you get back the same thing. If you do it once more, you get back the original. And you can rotate it and get back the original. And so this is one symmetry, this is one symmetry, and these two symmetries, they say, generate a group of symmetries of a triangle. So these are all based on notions of congruence, and entire group theory is essentially about studying these symmetries. So this is the other way in which in high school we see symmetries. I don't know whether this is so formally explained, but it could be when you're talking about symmetries of various objects. So here is a interesting ambigram. What do you read? It's a pentagon. So it's a pentagon like this. It's arranged like a pentagon, and you can see there is one of the symmetries is working the way you can rotate it. So by 2 pi over 5. So these are the two operations that we did for symmetry. Can you read the first one? And what about this then? Can you read that? So does reflect, this is reflect, does reflect have reflection symmetry? Does rotate have rotation symmetry? So you can see that if you rotate this around the middle, then you will get rotate back. And if you reflect this, you get reflect. Okay, here's a quiz.
Triangle.
Triangle? Any other? Translate. That's the answer. Okay, do you see that? So if you take the first set of hieroglyphics and you shift them, then you get translate. So the hint was that I said, can you translate this code? So I was asking you to translate it. If you translate it, you know what it is. Here's a popular object which has translation symmetry. It's a sine curve. So the periodicity, the translation is the periodicity. We study periodicity of various objects, such as sine, cosine, and then number theory they have objects which are doubly periodic, which were involved in the proof of Fermat's last theorem. So this symmetry, this translation symmetry is quite useful. It's studied a lot in mathematics. Okay, so next we go to another symmetric object. This is self-symmetry. So what is self-symmetry? Self-symmetry is repeating a similar shape at a different scale. So similar objects, remember similar triangles are two triangles which one can shrink or expand to fit the other thing. So they're called similar, and self-similar means an object which is similar to itself. And it is done repeatedly, so the point is that the part of a figure is similar to the scaled down version of the big figure. So here's an example of a square, which is shrunk by a factor of 1 over square root 2. So it's repeatedly, square, 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 and then this is an infinite object. So this idea is called self-similarity. And there are these objects called fractals which are studied in nature and which are good representations of objects such as very complicated and chaotic objects such as coastlines, for example. They are studied, they are modeled on using this. So a guy called Benoit B. Mandelbrot wrote a book called The Fractal Geometry of Nature, and then after that it's become a very active area of research. Not just for the graphics, but also for their applications in applied math and science. So self-similarity is quite interesting. So here is one for self-similarity. And if you come close, and so this is self-similarity, but if you come close, you will see that it's made up of self-similarity too. So this is made up of self. There's small selves which make self, and then this hyphen is self-similarity, and then this is made up of similarities. So that is kind of actually, in a graphic setting it's easy to do. They can just scale it and keep making it quite interesting. So here's another example. So you begin, this is known as a Koch Snowflake. So you begin with a triangle and you cut this triangle into 3 pieces. And in the middle third, you make another triangle like this. So do you see how to go from here to here? You take each side, cut it into 3, divide it into 3, and then the middle part you make a small triangle, 1/3 the size. Similarly, this side you make a small triangle, and this side you make a small triangle. Fine? So you know how to make a star? Okay, then take each of these guys, these sides, divide them into 3 equal parts, and then just make a little triangle over here, and then you get this. And this is another generation. So this is known as a Koch Snowflake. So you can see after just 4 or 5 iterations, the number of edges become bigger and bigger, number keeps increasing. Then you do even more, it will become finer and finer. Right? Here's another example. This is known as a what's it called? Symmetry triangle. So you take a triangle, take out the triangle, take out all these, and then keep going. So here's another Sierpinski square. So you have a square, then you take out the square, then you take out a small square. So I have a quiz question since I'm going very fast. Can you calculate the area of this hole? You have 2 minutes. Please calculate. In this final figure, if you keep doing it infinitely many times, calculate the area of the white spaces. Okay, please take out your paper and pencils, the math class.
2 by 9, sir.
Huh?
2 by 9.
2 by 9. Okay. Well, everybody's answer?
1 by 9. 1 by 9. 1 by 9. 1 by 9.
The line is this guy. I want the final. Do it like infinitely many times. Please give me the answer. Don't tell me half the answer. Huh? Can you calculate? Open, take out a pencil. Please. Okay, I got your answer. Somebody said 1 by 8, that's wrong. Somebody said 1 by 9, that is also wrong. Please calculate. So entire thing is assumed to be 1. So the square is a unit square. 1 by 8, somebody gave me 1 by 8. Yeah? It's wrong. 9 by 8? 9 by 8. Well, this whole thing is 1. So 9 by 8 is bigger than 1. So the whole cannot be bigger. Okay, 1 by 8. Who's answering 1 by 8?
1 by 8.
Please raise your hand. That's wrong. Don't answer it again. Who's answering 8 by 9? That's also wrong. Please don't answer it again. 1 by 9 is also wrong. Answer is 1. Okay. Very good. So if you calculate it, of course 1 by 9 is the first square. Then the second square, in the second square, you have these, 1/9 of a square, and you have 8 of these. So 1/9 of 1/9, and then 8 times that. Right? So it's 1 by 9 plus 8 over 9 square, and so on. 8 square over 9 cubed, and so on. And when you get it, so overall the answer comes out 1. So this is kind of remarkable fact about fractals, which is again a very good story to share with students. That in this case, and there are many such examples. If you just do, if you calculate, so a lot of these fractals, they have infinite surface area but finite volume, or finite area but the surface area is infinite, and so on. So they are very contradictory kind of interesting kind of objects. And in this case, for example, it comes out to 1. So which is remarkable that when you remove all the whites and counting all the whites, eventually you're going to get equal area. But there are going to be dots there. You can prove that there are going to be black dots too, infinite number of them. Okay, here is another one. So this is a graphic that I have made. Perhaps I've shown before. So this is Pascal's triangle actually, made with zeros and ones. So it's a Pascal's triangle. So when do you see any other pattern here? So this is a Sierpinski triangle too, right? So when you take a Pascal's triangle, remember Pascal's triangle where every element here is the sum of the top 2 elements. So these two ones will become 0. 1 plus 1 is equal to 0. So it's a binary Pascal's triangle. And if you take a normal Pascal's triangle and all even numbers you replace by 0 and all odd numbers you replace by 1, this is what you'll get. And you draw many such things and you see that a Sierpinski triangle emerges from here. So this is rather remarkable theorem which can be visualized and is easy to understand for. Okay, another quiz. So this is about Mandelbrot. I told you Mandelbrot is the person who brought this into, made it popular. He wrote a book called The Fractal Geometry of Nature. So this is a ambigram for Mandelbrot, for Benoit B. Mandelbrot, and B is his middle name. And the question is, what does the B in Benoit B. Mandelbrot stand for? Benoit? And the hint is in the graphic. Okay, are you giving up? Yeah. Yeah, it's a practice. So every graphic is trying to represent the concept. I mean, either that or something completely different. That is the whole point of it being. So what's the answer? IKEA? You almost got the answer.
I didn't want to give the answer. I wanted to give a hint.
Okay. So that's it. All right. Huh? Between? No. So IKEA is suggesting that you think about self-similarity as a hint. Oh, he told you that. Yeah, that's what got it. Okay? Give up? So you know how your students feel when you ask questions they don't know? And you make fun of them like I'm doing. Huh?
Very smart and my eyesight is becoming very
Bigger.
big. So many.
That's what we've done. So he's giving hint after hint after hint to you. So, okay, I'll give you another hint. These strange things, what do you think they are?
Bold.
Do you see what this is? In the graphics, this thing and this thing, what is that? This is actually my favorite ambigram, even though Punya doesn't like it so much, but it took me a while to figure out what it meant. So, if you look, this guy is a piece of this chap. And this guy is a piece of this chap. So he cut it somewhere here. Okay? You see that? You see this is a piece of this pie and this is a piece of this. So now if you if you go on and build this whole chap, it will, all over here, what will you get? So what's the answer? So what's the answer? Okay, that's close. So B stands for Benoit B. Mandelbrot. So his name itself is Benoit B. So this B, this is IKEA's in this B also is the same thing, Benoit B. Mandelbrot. So his name itself represented as a fractal. And this is a very common joke actually. What does B stand for? B stands for. It doesn't really stand for this, but this is a joke. Okay, so we move on to the next. Okay, so I can say this almost every, except for IKEA, I don't think anybody really got it, this one. But he didn't know the answer.
I'm not claiming any prize.
Okay, so paradoxes, these are also very popular and children, especially teenagers, they really enjoy doing that. If teachers do talk about paradoxes and apparent paradoxes in class, I think a lot of interest will arise because these are very legitimate mathematical ideas. Mathematical, and typically they lead to great advances in mathematics and even in philosophy of mathematics. So these are interesting stories to tell. Many paradoxes related to set theory, logic, notions of infinity. There are all kinds of paradoxes. Let me show you a very simple one. So this is known as the Infinities Paradox, where this guy is a Cretan from Crete who famously remarked, all Cretans are liars. So is he a liar or not? So suppose he's a liar, then he's lying. That means all Cretans are not liars, and he could possibly be telling the truth. If he's telling the truth, then he's lying. So this is known as the liar paradox. So in another form, there is an island which is full of knights and knaves. Knights always tell the truth, and knaves always lie. So a knave, a guy goes to a knave, goes to a person, and the guy says, who are you, knight or knave? So he says, I am a knave. That's a contradiction. He can't be. If he is really a knave, he would be lying, and if he's a knight, he would be telling the truth. So he can't. So this statement itself is not allowed in that universe. So this is known as the liar paradox, and there are various forms of this liar paradox, and it's kind of interesting. Another paradox is Zeno's paradox. So Zeno's paradox, there's a lot of stuff written here. I'll just explain it to you. So Zeno's paradoxes are about motion not being possible. So suppose you have to go from. So now I have to get off from the mic. I'll speak loudly. Suppose you have to go from point A to point B. I have to go from here to here. Okay, over here, or here to there. So I need to first go half the distance. Then I have to go half the remaining distance. Then I have to go half the remaining distance. So Infinities said, therefore motion is impossible because you'll never reach that. You're going from A to B, but you will never reach. That's fine. So I'm going from A to B, but first I have to go half the distance, then another half, so I'll never reach there. Right? So it was. So he brought about issues of infinity in this case. So another was about continuum. He shoots an arrow, or the famous one is a race between Achilles and the tortoise. So Achilles goes very fast, tortoise very slow. So tortoise says, since I'm very slow, give me a head start. So tortoise starts here, Achilles starts here, let's say. So in the time, then they start the race, they're both going this way. In the time the Achilles reaches where the tortoise was, tortoise has moved a little bit further. Then in the time that he reaches this point, the tortoise has moved a little bit further, and so on. So Achilles can never overtake the tortoise. That was his paradox. And similarly, there was one on the arrows. And so he brought about, he mentioned these things because they appeared to be paradoxical. So whenever you deal with infinity, there are some paradoxes which come up, and the classic one is called Zeno's paradox. So how they got resolved is that in mathematics there are objects which are infinite in nature, but they add up to maybe finite. So for example, this series half plus 1/4 plus 1/8 plus 1/16, it adds up to 1, right? So we teach these series. So one resolution is that there could be infinite processes which add up, or which can lead to a finite answer. And one needs to understand what is the meaning of infinity and be careful a little bit, and then we can get that. So here's an example of a proof by pictures. Have you seen this? So there's a square of side 1. You take half plus 1/4 plus 1/8 plus 1/16 and so on. All adds up to 1. Fine, shall we move on? Okay, so there's another card paradox. There's a card with statements printed on both sides. So the front statement says the statement on the other side is true. The other side says the statement on the other side is false. So the question is it true? So suppose this is true, saying the other side is true, but that is saying that it's false. So then it comes back to saying no, this is false. So So there's a contradiction. Similarly, you start with, okay, suppose this is false, that means the other side is false. That means the other side is saying that it's not false, it's true. So that's again a contradiction. So these, so this is a Jordan's paradox or card paradox, again type of liar paradox, more complicated, but it shows that there are many proofs in so-called proofs in mathematics where these kind of paradoxical statements came up, and then people sort of tried to work on various set theories and axioms of set theory to try and resolve this kind of paradox. So here's back to an ambigram. This is a one-sided Jordan's paradox. So it's a little bit advanced from Jordan.
This sentence is false.
So if you read it from, just look at the figure of 8 here. It says that these sentences, if you're reading it like this, it will read false. It will read like this. And here it will say this sentence is true. So the same sentence is true and false. This is like a Jordan's paradox. Do you get that? So it's Jordan's paradox, but placed on one side of the card using ambigrams. So it says this sentence is true, this sentence is false. But, which one is it? If it's true, then whatever. Okay, got this one? So again, it's an interesting story to share with students, these paradoxes. Okay, this is a famous one, Russell's paradox. So Bertrand Russell was a logician. He wanted to write a book along with somebody else, Whitehead I think, where they wanted to place every mathematical statement on a firm footing. So they worked into this, and eventually they gave up the task. It was too complicated, and they ran into some contradictions. So then it led to a big advance in logic. People said that maybe there are statements in mathematics which cannot be proved true. So there are statements, mathematics would be consistent, but there could be some things which are not true. And so there were some major advances thanks to the paradox itself is, so you have a set R of all sets that do not contain themselves. Okay, and does the set contain itself or not? So suppose it contains itself, then by definition there's something wrong because it's a set of sets that do not contain themselves. And if it does not contain itself, then by definition it must contain itself, right? So such a set R leads to a contradiction. Right? Everybody got that? Did you understand the contradiction? Yes? No?
Make it a bag. Instead of set, call it a bag.
Okay.
This is a bag which contains all the bags of the world inside.
That do not contain themselves. That is another bag. See, so yeah, so it's an interesting, yeah. So actually, what the resolution of this paradox is that one cannot contain a set. There's one sentence which comes in our 11th class book, which says that a set is a well-defined collection of elements. This well-defined essentially means that if I take an object, if I take an element, then I must be able to tell whether it belongs to a set or not. And this well-defined was basically introduced thanks to Russell's paradox, because Russell's paradox is something where you can't decide whether it belongs to something or not. So in fact, category theory a little bit, more generally, people started looking at sets of sets which are collections of certain objects, and they tried to, distinguish between this whole thing of self, bag containing itself, or a set containing itself or not itself. That was sort of banned from math after this thing. So Russell's paradox actually led to a large advance in logic and the way we write things, and eventually it led to a simple set theory which a mathematician can use without really necessarily getting into these issues. But this was really interesting and important. So here's some more graphical paradoxes. So you must have heard of an artist called M.C. Escher. So he made impossible or contradictory figures, and I'm not going to show you MC Escher's artwork. So I'll just describe them to you. Some of them were like impossible figures, like you see a castle and a person going up on the stairs, but all around it's going up. It's not coming down at all. So it just looks that way. So they're like impossible figures, but they look very plausible. So they're very interesting, and students find them very interesting, especially if you tell them try and make something of your own. They find it even more interesting. So here's an example. This is called an impossible object. It's called a Necker's cube. So it's not clear whether this guy is outside the cube or inside the cube. It's a sort of impossible cube. This cube. Sometimes it seems that it's outside, sometimes it seems like he's sitting inside, depending on how you look at it. So this is the object, this is the impossible cube. It's called Necker's cube. And this is at the heart of MC Escher's drawing. So if you're sort of walking along this guy and suddenly you're inside, suddenly you are outside, that. But it seems plausible. Okay, so here's an can you read it? MC. This is an impossible font. The entire font has been made up of impossible figures. All of them. So MC Escher, it's kind of like a each font, each member of the family is. Okay. So then finally, I'm at the end of my talk, a little bit early in fact. There's a famous problem in Greek antiquity called squaring the circle. So the problem is you take a circle and you make a square of equal area, but you are allowed to use a straight edge and a compass. So you're allowed to use a ruler and a compass, as in the thing, and you're only allowed a finite number of steps. So this problem can be solved in infinite number of steps, and circle squarers. It's an impossible problem. So it was proved. They proved it that it cannot be solved. So we found a solution of squaring the circle. So can you read outside? Square, but it's a circle, right? So I've squared the circle. And what's here? It reads circle. So what's written here? Circle. What's outside? Yeah. But this is a square, this is a circle, so it's squaring the circle. So we've solved an ancient Greek problem. I think we should be given some award for this, but I don't think that we. Thank you very much.
That wonderful presentation showed such wealth of ideas, and I think what we need to see, Gaurav, is how we can convert these tasks which can actually be done. And floor for questions.
How will it construct it?
So it's, yeah, that is the.
What can, if we were to ask or if we were to try doing it by hand, what exactly? Should we look at a mirror reflection kind of a thing and then start off what are the type of, how do we motivate or how do we guide children to try? Because unless we make one,
Creating everything.
creating ambigrams.
That's the best.
Yeah. So it's an art form, but it's not. So I can tell you how Punya started. So Punya and I both were in high school together, and we studied together, and then he found a book, or his uncle gave him a book called Gödel, Escher and Bach by Douglas Hofstadter. So the book had very many interesting ideas, such as ambigrams, such as Gödel, logic, Russell's paradox, infinities, Zeno's, all the things that I'm talking about. That book had a lot of things, and it sparked our imagination. And some of them were graphics, and they were anagrams, palindromes, stories, all kinds of very interesting stuff. So it's highly recommended, the book, for you as well as your students. It's a classic. Now it's like 30 years old now. In that book there were these ambigrams. So he started making, and we all started making palindromes. So we've actually had one of our articles which got rejected was a complete article, was a palindrome. So it reads the same from front to back and back to front. Now a mathematician sees such things. I mean, we have proofs of if condition which look almost the same as, when you go backwards, it reads the same. And a lot of the main easy proofs in maths are all like that. They're extremely symmetric. So they are mathematical ideas, or some mathematical beauty is there. And similarly, so he just started making it. So just sketching. And then when he sketched it, then these have become, of course, more and more complicated as time went by. But if you sketch, you will see, how to write A as E. So the simplest is you take your own name, or take some simple name, and you try to see it. So I took my initials, for example. It's very easy to do G and B, so if you go to Punya's site, you'll see. But if you look at just the B and G here, that's very easy. So you can get started with small stuff. Try S and G, for example, to see whether you can do it, try to write G as S and as a reverse, and you will find some solution. Many times what Punya says is that the solution seems unique to him. That's the best way to do it somehow. So as an artist, he's able to do that. But he has tried it in workshops, because he's able to guide students. So he teaches teacher education in Michigan State. So he has his own classes. He's asked students to make, poems, graphics, and they're able to do it. Some of them are able to do it. So they may not be finished products like a real artist, but the basic idea will be there. So, my suggestion is, don't tell your students, I don't know how to do it, but see if you can come up with it, and you will be surprised. You will get some nice. And poems, certainly it works like a charm. I've tried that. Poems, there are a huge number of interesting limericks, poems, all mathematical ideas. Say that, make a poem on some mathematical concept, whatever you like, small, big, whatever. Show a few examples. There are lots of examples on the web. And then they're all interesting. And then it sort of helps them deal with it. So Punya actually published at Right Angles a long poem on the complex number I think, right? So that was like really a huge poem. And but a lot of people, some proofs of infinity of primes, that kind of, the proofs of that which are sort of written as poems. And these are interesting mathematical activities. Kids will suddenly say, oh, so math guys can also have fun, That's the main thing.
I found Fisher's work, how he did some of things. It's very limited.
Very good.
Just with pencil and straight edge, he created all the lines. So there was nothing available.
Yes.
And it's available somewhere on the website. When you search it, all the ideas did it.
He also had lithographs, and they're amazing one. So famous Escher's painting is man drawing a hand which is drawing itself. So it's like that liar paradox, which is real. It looks really real, and the other one looks like a drawing. So brilliant.
The
And
transformative theory is that we take something, it transforms into bird, into mouse.
right.
It comes back to the bird.
Yes.
Also, Escher has done a lot of tessellation work.
Tessellation.
The-
Yes, that was the bird thing is very brilliant.
And the lizards. There are multiple lizards scissors which interlock with each other and dial the blade.
Yeah.
So I
The
think
Pankaj Symmetry, we
Yes.
are on that also.
Yes.
these can be brought to the classroom so children can start, when they study shapes, they can do tessellations and then they observe.
So I think the broad theme is that the idea is playfulness and fun. Now, it can happen in mathematics classes a lot more than it does now. Right now, we are often focused on procedural learning, even if, getting the idea and all that, but there is a aspect of fun, which we know. See, we would not have been sitting in this room if we didn't have fun, right? It's not that we are a dull old, this thing with no fun in our life, we're just doing these problems, getting the right answer. There is some chemical reactions which are happening in our brain when we solve a problem, we have fun. Now that experience one has to give in different ways, and I think that this is one of the suggestions there.
I liked your idea of, so I wanted to know about self-similarity. So did you, the self-similarity which was created using the idea of self-similarity. So possibly there could be other mathematical ideas and processes which can be represented using ambigrams, but to identify these itself would be a very interesting task.
Yeah. So that's my job. His job is to create it, and my job is to say, can you make this? I want a sine curve which looks like a sine curve. so then he's struggling with it. But this is our collaboration. So he makes ambigrams all the time. Then for some reason we started writing in this math article series. So of math and art. So then my job was to make sure that the article has some math in it. So then I was explaining about symmetry, this, that. Then it was sparking ideas in his head on how to do different ambigrams. So for example, things like inverse or exp and log, these are remarkable because they are exp is becoming log, and it is exactly the symmetry that you can expect. So these kind of ideas, so we keep, so next one is on infinities. So we're still figuring out what to do. But it's an interesting thought process. I think by doing mathematical stuff, he is also, as an artist, he's got a lot more challenge to make sure that the form is equal to function. So we also have examples where the form is not equal to function. So there are contradictory ones which I haven't shared. So for example, in self-similarity, instead of in self, the one which I like more is where the self is written with similarity and similarity is written with self. So it's not self-similar. It's parts of it, it looks similar, but it's not. It's not contradictory.
So I think we would like to thank Gaurav for their wonderful presentation.
Thank you, sir. I would like to request Janki Ghosh ma'am to felicitate Gaurav Bhatnagar sir. Thank you. Now, there are two small announcements. The first one is that there are some changes